Provide an introduction to section 13.2, the chain rule, with an emphasis on the moment on examples just using polynomials. We've kind of bypassed one of the first sections, and so that's why we're just going to focus on polynomials since we didn't cover section 13.1 quite yet. So with the chain rule, we're going to start looking at more complicated functions and taking their derivatives. Excuse me, but before we start, I want to just kind of review a couple basic pieces. And what I'd like you to do here is do nothing more than just kind of use the power rule. If I said f of x equals x squared, and I asked you to tell me what f prime of x is, most of you will go to the power rule pretty quickly and tell me it's 2x. If I said f of j happens to be j squared, you'd probably tell me f prime of j is equal to 2j. And most of these would roll pretty quickly. If I said f of z equals z to the fourth, you'd be tempted, and you'd be pretty much right, to say what? That would be nothing more than 4z cubed. And then I did something that looks like a little bit of gibberish, but again, just remember, I'm just giving a variable a different name. This variable happens to be a little bit longer, but it's still a variable. So if I said f of something was equal to the function something to the 9th power, I said, please take the derivative of f prime of something. You would tell me it's equal to 9 something raised to the 8th power. That's what you kind of do if you just intuitively looked at the power rule. Again, what's in here almost is immaterial. Whatever here, whatever was there, what did I write? Hey, look, z cubed. What did I write here? J to the first. Did I bring a 2 in front in the first two? Did I bring a 4 in front? Yes. Did I bring a 9 in front? Sure did. And then what did I do? Whatever my variable was, x, j, z, or something, I just decremented the power by what? By 1. X squared. X to the first, j to the first, z to the fourth, z cubed, something to the 9th power, something to the 8th. And so what I asked you to do next is work through a few examples. I gave you some derivatives or functions that look just kind of the same way. They're functions that we understand that we could expand, but I wanted you to just kind of treat them like the same thing we did on the first page. And just whatever's in here we'll call our something. And so if I did that same type of pattern as we saw on page 1, I would say f prime of x equals 2 times x squared to the first, or 2x squared. I'd come over here and I would say f prime of x equals 2 times x minus 3 to the first. If I simplify that, I'd have 2x minus 6. And if I went over here, I would say f prime of x equals 4 times x squared to the 4 minus 1 to the 3rd power. I come back with an answer of 4x to the 6. But what I then asked you to do is take those same, let's see if I can just move this just big enough that we can see this. I'll hold up my camera. I said, forget the parentheses, let's go ahead and expand each of these things. So x squared squared became x to the 4th, and if you took the derivative of that, you'd have 4x cubed. If you took the derivative of x squared minus 6x minus 9, you'd walk into 2x minus 6. If you took the derivative of x to the 8th, you'd walk back with 8 times x to the 7th. What I next asked you to do is kind of compare the answers. 2x squared against 4x squared. 2x minus 6, 2x minus 6. 4x to the 6th, 8x to the 7th. And I asked you, are they off by anything? Well, yes. To get, these are the true answers, by the way, down at the bottom. 2x squared to 4x cubed, I'm off by a factor of 2x. So I'm going to just kind of break these things up very quickly. My derivatives matched. I'm okay. 4x to the 6th, 8x to the 7th. How much am I off by again? I need 2x. And what I asked you to look at is, think about it. I'm off by a factor of 2x. A factor of 2x, and gee whiz, I'm good. Or I could say, hey, I have a factor of 1 if I want to. I know that sounds funny, but here's what I'd like you to think about. What's the derivative of the thing sitting in here? 2x. What's the derivative of x minus 3, the thing in the parentheses? It happens to be 1. What happens to be the derivative of that x squared? Well, again, it's 2x. And what I notice is my answers, my official answers, are correct. My, hey, just kind of used a power rule and gut feel my way through it, are off by a factor that is equal to the derivative of what's sitting inside the parentheses. Now, I asked you to do one more problem of that same ilk. and it was of this nature. I said f of x equals 4x squared minus 3 squared. And if we did our good old, hey, let me just guess off the power rule, I'd say I'd have 2 times 4x squared minus 3 to the first power. 8x squared minus 6 is what I think I'd look at. Let me just make sure. That's what I think I would have happen in here. Now, if I go and look down here, if I expand what's in the parentheses, as I do as a normal polynomial, 4x squared minus 3 times 4x squared minus 3, 16x to the fourth minus 24x squared plus 9. What's the derivative? 64x cubed minus what? Minus 48x. And let's think, compare this versus this. The official answer is down here because that certainly is what that polynomial gets expanded to. So our little just kind of feel our way versus the true answer, what do you notice we're off by? We're off by a factor of 8x. And, by the way, look inside the red parentheses. What's the derivative of 4x squared minus 3? It's 8x. So what I hope you're noticing is some of these functions that we have are relatively complex. They have some relatively complicated stuff inside of them. If I think about this is, we'll talk about it in a few moments, but this is like a composition of functions. On the outside, I have just the good old squaring function. On the inside, I have something that's a little bit more complicated, 4x squared minus 3. And so what we're going to start seeing is the thought of an outer function, a squaring function, and an inner function. And we're going to have to combine those derivatives. Think, what was the piece that we were missing here? We are missing an 8x. It happens to be what? The derivative of what's sitting inside. If you look at 2 times 4x squared minus 3, that's what in our crude way we would think, hey, that's what the power rule, if we just took this thing at face value, called this our good old something again, what would we say? Hey, it would be 2 times something. Hey, inside the parentheses, 4x squared minus 3. There's our something to the first power. Nice, that's a good part of the final derivative, but what's it missing? The derivative on the inside. And that's what the chain rule is all about. So let's do a little bit more work, a little bit of notation here. And we're going to come back with our good old Leibniz notation, just to make sure there are a number of ways in which the derivative has been written. I'll just go ahead and handwrite it for a second. I'm just going to put it on the side of this piece of paper, so don't worry, I'm just going to reuse what we already have. We've said when y equals f of x, there's a bunch of ways we write the derivative, y prime, f prime of x, and then the one that's going to be important to us is dy dx. This is good old Leibniz notation. Has a lot of algebraic pieces that we're going to find out. So let's take a look at that using Leibniz notation to help walk our way through the chain rule. So take a look at the following. When y equals f of x, just a function, y as a function of x, we have a derivative as dy dx. And we would say that is what? The derivative of y with respect to x. When s equals f of t, hey, there's just a different function. Maybe s is speed and t is time, or whatever it happens to be. Our derivative in Leibniz notation would be written as ds dt. S is the dependent variable, t is the independent variable. Y is the dependent variable, x is the independent variable. This second derivative, we say it's the derivative of s with respect to t. And that again is Leibniz notation. Now, let's do something a little bit more complicated. We're going to start talking about that inner and outer function. I'm going to say that y can be written as a function of variable u. Y equals f of u. The derivative of that would be written as dy du, y with respect to u. And now I want to compound things, and I want to say y is a function of u, but in turn, u can be written as a function of g. So I'm going to say u equals g of x, and the derivative of this function happens to be du dx. And so, with the two statements being true, we're basically saying, repeat one more time, just write it, y is a function of u is a function of x. How can we write y as a function of x? Y a function of u a function of y. We can do that as a compound function. So take a look. y equals f of u, u equals g of x. There's a substitution. So it's not a problem to say y as a function of x is nothing more than y equals f of g of x. And so take a look. You have two functions operating. You have an outer function, the f function, and you have an inner function, whatever g happens to be. And with this structure, well, can we compute dy dx? Well, the answer is, yeah, we really can, and it's through some basic algebra. The derivative of y with respect to x, that's what dy dx is. Take a look at some basic algebra. Dy dx is nothing more than dy du. The first derivative that you see up here, y with respect to u, times du dx. Again, what happens? Our two du's are canceling each other out. And this is a clean and a very nice algebraic representation to show when we have y not directly written, we can't quite see the function, but when we have a pure composite function, the two derivatives, the derivative of the outer times the derivative of the inner, will give us exactly what we're looking for in terms of the final derivative of y with respect to x. So we're going to use the concept of substitution very, very frequently with this. So saying it one more time, when y is a function of u and u is a function of x, the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. And this is the chain rule in a nutshell. Now, there's some different statements that you might see. The book might do this. You might say, hey, instead of f and g, I'm going to say y equals an outer function, and that outer function works upon an inner function. It takes an inner function as its input. And so I can say y prime, the derivative, is the derivative of the outer function evaluated at the inner function. I know that sounds a little funky, but you'll look at that and you'll see it a little bit. That's kind of if you go back to the beginning, when I said we're kind of taking the derivative of something, where we're kind of using that power rule, but not just kind of on intuition at the beginning. That's kind of what we're doing here. Times what? The thing we talked about that was the missing piece, the derivative of the inner function. Another way to write it, if f of y equals f of g of x, we can say y prime is equal to the f prime, the derivative of that outer function, evaluated at g of x. That's what we're saying, right? The derivative of f evaluated at g of x times what? The derivative of g evaluated at x. And this is going to be different forms, different ways you see it in the book. My own general feel is the one that's going to make the most sense to you because we're going to do a lot of work with substitution to begin with. Over time, you're going to feel your way through the chain rule. With a little bit of practice, you'll be able to kind of do this with a fair amount of intuition. But for the moment, we're going to use what we'll call a technique called U substitution that's going to make this work very cleanly for us. So let's do that via some examples. For the moment, focus is just going to be on polynomial derivatives using the chain rule. We'll be doing more complicated derivatives with things other than polynomials pretty soon. So in my first case, I have y equals 3x plus 6 cubed. We're going to look for a parent function y with respect to u, and the outside the parentheses is our parent function. Our outer, I can say, is y equals u cubed. And how do I write u? I can write u as u equals 3x plus 6. There I go. There's my outer function, which is the cubing function. What's the thing that I need to cube? What's my u? 3x plus 6. So how will this then work? Well, what can I say? What's the derivative of y with respect to u? dy du equals 3u squared. Du dx is the derivative of 3x plus 6, u as a function of x, which is nothing more than 3. Multiply the two together and I would have dy dx equals 3u squared times 3, or 9 times u squared. Now, since I want everything in terms of x, having the variable u floating around isn't the most friendly thing in the world. And so what can I say? Substitute back in. What do I know about u? 3x plus 6. dy dx equals 9 times 3x plus 6 squared. Now, do one quick thing. We'll talk about some intuition. If I just kind of tried to build this on myself, I would do what? Hey, power rule would tell me 3 times 3x plus 6 squared. It looks nice. What am I missing? I'm off by a factor of 3. And so what's the other thing that I was missing here? I need to take the derivative of what's sitting inside here. Derivative of 3x plus 6 is nothing more than 3. So again, we'll start to intuit our way and feel ourselves through this, and this walks me right into that same 9 times 3x plus 6 squared. But for the moment, let's work with u substitution, because I think that's a good, clear way to see these to begin with. My inner function, I can see it. My outer function is the squaring function. Y equals u squared. dy du equals 2u. My inner function is u equals 4x cubed plus 2x squared. Excuse me. U is 4x cubed plus 2x. I'm sorry, it's just what's inside there. Apologize for that. Du dx is nothing more than the derivative of 4x cubed plus 2x is 12x squared plus 2. Dy dx equals, what would we have in this case? I'm going to have 2 times u times, in this case, 12x squared plus 2. All right, what's u? 2 times 4x cubed plus 2x times 12x squared plus 2. I'm not going to worry about expanding this out for the moment. We'll just kind of work and just let the numbers kind of hang as they are. It's a good enough representation for right now. Take a look again. What? Hey, here's the 2. 4x cubed plus 2 to the what? 2 minus 1 power. And then what's the derivative inside? 12x squared plus 2. There are the pieces. All right, 2 more to go. Y equals the square root of x squared plus 4x. Well, in this case, let's just do something. Y is equal to the square root of u, or u to the 1/2 power. U is equal to x squared plus 4x. dy du equals 1/2 u to the negative 1/2. Clean that up in just a little bit. Du dx equals 2x plus 4. So let's do a little bit of work. 1/2, 1 over the square root of u to the negative 1/2, times 2x plus 4. I'm going to have a 2x plus 4 over 1/2. That's going to become x plus 2 over the square root of u. 2x plus 4 and a 1/2. And what's my last piece? Dy dx equals x plus 2 over the square root of x squared plus 4x. Agreed, that's a ugly as all get out derivative. It is a legitimate derivative nonetheless. Last one to do. 3x squared minus 6x plus 1 raised to the 3/2 power. Outer function is u to the 3/2 power. Dy du equals 3/2 u to the 1/2, or 3 the square root of u over 2. U equals 3x squared minus 6x plus 1. Du dx equals, in this case, 6x minus 6. Dy dx equals 3 square root of u over 2 times 6x minus 6. The 2's, well, that'll be nice. I'll wind up with 18x minus 18 over 2. So I'll have the square root of u times 9x minus 9. And what's my last piece to do? Get everything in terms of x. dy dx equals the square root of 3x squared minus 6x plus 1 times 9x minus 9. So there's a lot of power here. There's a lot of stuff here, I freely admit with this. But with these u substitutions, you now are at the stage where you can take derivatives of some pretty complicated polynomials. Be good with this substitution technique. Y as a function of u as a function of x, respective derivatives, y with respect to u with respect to x, multiply them together, and you can obtain the thing you're searching for, the derivative of y with respect to x.